Professor Guturman, you can start seminar.
Okay. Okay. Welcome everybody to our European non-associative algebra seminar. And our speaker today is Susanne Pumpluen, and she will talk on a way to generalize classical results from central simple algebras to the non-associative setting. Please.
Thanks for the introduction, Alexander, and thanks very much for the invitation to have me speak. So what I want to do today is I want to give you an introduction to a certain theory, which is very new and very old at the same time, and basically talk about a certain class of non-associative algebras, which I've been working with for the last 10 or so years. And these algebras have now gained again some momentum because this summer a paper appeared on the archive, which is from Blachar, Haile, Matri, Rein, and Vishne. And they started to investigate what they called semiassociative algebras and used these to define a generalization of a Brauer group, but for non-associative algebras. So my talk will be of two parts. The first part of the talk, I will first talk about, well, these algebras, which I found always interesting because they're generalizations of the classical cyclic algebras we all know. Central simple algebras, cyclic algebras are certainly one of the most important central simple algebras. And the second part will then be, I will briefly introduce the theory of Blachar, Haile, Matri, Rein, and Vishne, and then see how these algebras slot into, because these are actually examples of semi-associative algebras, so how these fit into that theory and how, because these algebras already were very similar in behavior to the classical ones, actually again appear as very similarly behaving to the cyclic algebras in the Brauer group. So I will start very easily, very slow. So let me just sum up what I need from non-associative algebras. I take F to be a field. And when I talk about an algebra, in this talk, I will only talk about unital algebras and finite dimensional algebras. And when I say algebra, I mean an F vector space A together with some bilinear map, which gives me the multiplication. So I'm not assuming anything. And then according to if that multiplication is associative or commutative, I will call the algebra associative or commutative. And as I said, it will always be unital in our context today, this algebra. So since we're assuming that the algebra is finite dimensional, we will always be able to say that it is a division algebra if it's non-trivial and doesn't have any zero divisors. So that means if I have some x times y equal to 0 in this algebra, it will automatically mean that either x or y have to be 0. And then, of course, there is this way to measure the, well, associativity or not associativity of a non-associative algebra. And for this, we use the associator. And then we have the left, middle, and right nucleus. And these three are actually associative subalgebras. And their intersection of all three of these, the intersection that is called the nucleus, again an associative subalgebra. And this is a very important subalgebra to know because it does not change under automorphisms or isomorphisms, and basically is what we will focus on a lot today. Because when you think of how you want to get any kind of idea on this vast class of non-associative algebras, which is out there, of course, you can try several different methods. You can try to look at the derivations. You can look at the automorphism groups. You can do God knows what. And one approach which is actually very kind of promising, which I have been kind of employing for the last years, and now the others too, is to actually look at the nuclei, to look at non-associative algebras which have certain nuclei, and hope that we get a bit of a better idea and understanding how these algebras behave and how they look like. And so, of course, when we look at the classical theory, there is this Wedderburn theory on central simple algebras. And so we have certainly, if we want to generalize this, we should definitely look at central algebras too. And so what does it mean that an algebra is central if it's non-associative? Well, it's basically the same definition, just that we have to be a bit careful. So the center of an algebra now is again all the x's in that, all the little elements in that algebra which commute with every other element, but also lie in the nucleus. So that is then the center of an algebra. Okay. So I want to kick off by looking at the classical Quaternion algebras. So for this, for now, I assume characteristic of the base field is not 2. And I take a quadratic field extension K. So just adjoin some square root to F. And then I can do, well, you probably know this, there is something called a Cayley-Dickson doubling process. And that is one way to define a Quaternion algebra. So this is the one I chose right now. So if I'm taking this quadratic field extension K plus K, this is a 4-dimensional vector space and becomes a 4-dimensional unital associative algebra over F, if I take the multiplication I wrote here, which is the Cayley-Dickson doubling, where I'm employing the non-trivial automorphism sigma here in writing down this multiplication. And what I get is a Quaternion algebra. And there are 2 ways of writing this in the literature. There is the way just to write A, B, where A is here the root of A I'm adjoining, and the B is the one which is the little factor here in the multiplication. Or I can write it as a cyclic algebra of degree 2, which it is in this notation here, K over F sigma B. So this is a cyclic algebra of degree 2. It's called a Quaternion algebra. And the most prominent example is probably Hamilton's Quaternion algebra, where I have the complex numbers over the real numbers, complex conjugation, and my B is -1. Okay. So I think this is all known to all of you. Now, what happens if I'm kind of optimistic and choose the little scalar here, the B, which usually lies in F and is non-zero? If I choose this in the bigger field, in this quadratic field extension that I'm using in the doubling process, what happens? Well, nothing happens, because the multiplication, of course, is still well defined, because it makes sense what I'm writing here. I'm taking exactly the same multiplication. I'm taking exactly the same 4-dimensional vector space. I will again get a unital algebra over F. And this algebra now is called a non-associative Quaternion algebra, because it's actually highly non-associative. And one of the many interesting things about this algebra is that it behaves eerily similar to the classical Quaternion algebra. And for instance, the automorphism groups, there are lots of inner automorphisms. If you define inner the right way, 2 of these algebras are isomorphic if and only if the conditions are basically the same as the ones from Albert and Jacobson, the classical ones. And most prominently, probably what is different, however, is that this algebra will always be a division algebra over F, no matter the choice of B, which is in stark contrast, of course, to the classical case where we have to be careful how we want to choose the B, because the thing could be the 2x2 matrices. So what is perhaps even more surprising is that the example, if I'm going back to the real numbers as the base field and I'm looking at the complex numbers as the quadratic field extension, and I take B to be I, that this is a real division algebra, which was actually, to my knowledge, the very first example of a non-associative division algebra in the literature, and it goes back to Dixon to 1935. So this is not even a new algebra. I just wrote it in the modern way. And these algebras were then actually rediscovered pretty much around the same time by Althoven and Kugler, just over the reals, and then by Waterhouse in 1987. And then Vincent Astier and myself, we wrote a paper on it, but we generalized them over every ring, basically. We looked at them not over base fields, but over rings. And then basically they were kind of forgotten again. And then I started working a bit with coding theories, space-time block codes, and I realized that certain algebras the engineers constructed very painstakingly could actually be seen as non-associative algebras. And I realized that the algebras behind these codes that the Indian engineers fabricated were non-associative Quaternion and then actually non-associative cyclic algebras. And that brings me to the next topic. Of course, we know that Quaternion algebras are the easiest example of a cyclic algebra. So now, can we generalize cyclic algebras as well? So if we have a cyclic field extension of degree m and the cyclic Galois group generated by some sigma, can we now also take the classical construction of a cyclic central simple algebra of degree m, and instead of choosing our usual little, I don't know, scalar d, which we need in the construction in F, can we choose it in the bigger field K? And the answer is yes. And again, we get non-associative cousins of our cyclic algebras, which behave ridiculously similar to the associative ones. And now that brings me to the next section, because I have to make a tiny detour. I have to bore you a bit with skew polynomial rings. In order to properly introduce this generalization, I will need to talk about skew polynomials. So for this, I take some D, which is a central simple algebra over F, and an automorphism sigma, and I take a left sigma derivation of D delta. So sigma derivation means it's an additive map, and we have the identity, which you can see here. And then I define the skew polynomial ring R as the set of all the polynomials with coefficients AI and D, where I have the addition defined termwise, as in for normal polynomials, and the multiplication comes with a twist. Because the multiplication now takes into account that, well, if I have t times a, I can't just pull over the a on the other side of the t, so that would become sigma of a times t, plus if the delta is not 0, I would also carry now a delta of a. And that would define me this little equation, how to multiply two polynomials in a skew polynomial ring. So the elements in a skew polynomial ring are called skew polynomials. And the ring itself, with this definition, is an associative non-commutative ring. So one special case is when delta is 0. And that's the one we will look at mostly today. And that's also called the twisted polynomial ring. And then, of course, you can see that the multiplication here becomes a bit easier because this here is just gone because this is 0. So then we have TA equals sigma of AT. And the easiest example for this is probably the ring of left polynomials, because that's exactly the ring where we have the usual multiplication of two polynomials, just that we have to be careful because these are polynomials with the AI and BIs. They are in D, and D is not commutative, so we have to be careful. But generally, the definition is otherwise is the same. And that's exactly the case where sigma is the identity and delta is 0. And that is also denoted by dt in the literature, or sometimes d sub L. So why I'm doing this? Well, I needed these skew polynomial rings so that I can show you now how to construct non-associative algebras in a very canonical way using skew polynomial rings. These algebras go back to a French mathematician. They were invented by him in 1966. His name is Petit. And they were pretty much forgotten then because he didn't publish. It was only a seminar preprint. He didn't really publish it. And then people who work in finite fields kind of found them and then worked with them because they're very important examples of semi-fields. And then Brauer and Skew wrote a very nice paper, and also then they came, and I came then with the from the coding point of view, from the space-time block codes, and then we kind of I started working with these algebras. And the funny thing is, and perhaps I'll tell you that a bit later, that they're implicitly in the literature, but people often didn't realize that they were not working with an associative algebra, but with a non-associative one. So anyway, so let's see what I do, or what Petit did. So he takes a monic polynomial. Monic is the same definition as when we have normal polynomials of degree m greater or equal to. Degree is exactly the same definition as for normal well-known polynomials. And then there is some kind of Euclidean right division algorithm, and that goes as follows. For all G, all polynomials, I can find unique R and Q, where the degree of R is strictly less than the degree of F, such that G is Q times F plus R. So when I'm taking, I can take any G divided by F, and there is always a unique Q and a remainder R. So that, however, since we're working in a non-commutative setting, well, we have to be careful. So here I'm right dividing by F. So that is something one has to be very mindful that we're working here, because that's also, it says right division algorithm. There's also left division algorithm. We're doing the right one. And so when we have a two-sided ideal that is generated by our F, if we take the ideal RF, which is of course one-sided, but if this happens to be two-sided, then we get a very familiar situation. We're getting the usual quotient ring R mod RF. We are modding out the two-sided ideal out of the non-commutative ring. But what happens if this ideal RF is not two-sided? And this is what people didn't see. Because, of course, everybody will immediately go, yeah, then it's a left R module. We still have a structure, of course. We still have a structure on R mod RF. We have a left R module structure on it. But we also have a non-associative ring structure. So this was done over fields, and basically assuming that the D is a division algebra, one can generalize it as long as the F is monic. So if we're taking the remainder of right division by F, which would be our little r in this equation here, then we can use this to define a multiplication. And we use this to define a multiplication on basically what we usually call R mod RF. So what we're doing here, to be very precise, let R sub m be the set of all the polynomials of degree strictly less than m. And then we have the usual addition of polynomials. And we have the multiplication, which is basically saying if we take two polynomials which have degree strictly less than m, multiply them, what's the product? The product is exactly the remainder of whatever we have when we do g times h, but compute modulo and divide by f from the right. And this becomes a unital non-associative ring, and that is usually called S sub f, or Petit algebra, because it's an algebra over the subring of all the A in this central simple algebra D, or associative algebra. Usually it will be a central simple algebra or a field extension, this D, where we have AH equals HA for all the H which have degree strictly less than M. That's a subring, unit commutative subring of our D. This subring, this non-associative ring, appears in several classical papers on sigma delta codes, but people often didn't realize that they were actually working in a non-associative setting. So this algebra is actually associative if and only if the F generates a two-sided ideal. And in that case, we're back to the classical quotient algebra, and we're just factoring out a two-sided ideal. So this can be viewed, this construction, as a very canonical way of generalizing this classical quotient algebra. So I want to make very clear that we understand what is irreducible here. So if I say F is an irreducible polynomial in this context, that means it's not a unit and there do not exist G and H of degree strictly less than F such that F is the product. So the way we would expect reducible to be defined. Now, irreducible polynomials are very important now because they are the ones which will give us the algebras which have no zero divisors. So this result goes back to Petit. So say we have a division algebra, D, and say our algebra is not associative. Then we immediately will know that the left and the middle nucleus will be D, so that is not very interesting. The right nucleus is going to be the eigenspace of this polynomial. So the right nucleus is very interesting because this right nucleus here encodes a lot of the information on the polynomial F. And if F is irreducible, this right nucleus is a division algebra. If SF is also finite dimensional, which it does not need to be because it could very well, I have lots of examples where this algebra is infinite dimensional over this field F naught. Well, if it's, however, finite dimensional and F is irreducible, then this SF is a division algebra. So this is a very elegant way to produce a large class of division algebras. So this also ties in with questions where you can see if you already have some ideas from perhaps people who work with factoring. You can use this for many things, for factoring, skew polynomials. You can use it for understanding the ideals in these algebras, which then will actually be related to the sigma delta codes again. So there's a rich theory here. No time to talk about this, unfortunately. So let's just go back to my easiest example where I have complex conjugation and my field extension complex numbers over the reals. and I want to look back at the non-associative Quaternion division algebra from Dixon. How does this tie in now with these skew polynomial rings? So if I'm looking at the non-associative Quaternion division algebra, which I get when I take the I for Dixon, you can see that this is actually, one can show, this is just the skew polynomial ring where I take the polynomial t squared minus I as my f. This is an irreducible polynomial, and this is exactly Dixon's Quaternion division algebra here. And of course, the classical case, Hamilton's Quaternion algebra, is probably known to everybody. That would be the case where I take for sigma also, of course, complex conjugation, and then I take for f the irreducible polynomial t squared plus 1. So you can see this is another way to introduce Quaternion algebras, classical Quaternion algebras. And if you do it this way, you can also see how nicely the generalization of a non-associative Quaternion algebra fits in to this setting. So that brings me to non-associative cyclic algebra. So these were, to my knowledge, done for the first time over finite fields by Sandler in 1962. And then my student, Andrew Steele, started to generalize these for any fields and also found some additional results. And that was basically his PhD thesis. And this is why I needed the skew polynomials, because the easiest way to define these is to say, I take a cyclic Galois field extension of degree m, k over f. The Galois group, say, is generated by sigma, and I take some element d, which is non-zero in the field extension k. And now I'm taking these Petit algebra construction so that I take the twisted polynomial ring k t sigma, and I'm modding out the ideal that is generated by the polynomial t to the m minus d, where m here, the t to the m is exactly the degree of the field extension. And this algebra that I get this way, I call k over f sigma d. And then it's very easy to see that if the d lies in the base field and is non-zero, I get an associative cyclic algebra of degree m. If it lies in k and it doesn't lie in f, I get a non-associative algebra, and this non-associative algebra we call a non-associative cyclic algebra of degree m. This algebra, again, of course, we know now, has left and middle nucleus k, and the eigenspace of this, the right nucleus, is a subalgebra that contains k. So the nucleus of this thing is k. If you want to directly define it and just don't think about twisted polynomial rings, you can also just write down the multiplication straight away, which I did here at the bottom of the page, like this. So we can avoid doing the skew polynomial rings, but I have a reason why I didn't, which becomes apparent towards the end of the talk. So this is the first part of my talk. So this was my stuff. And now for the second, I would like to talk about the super elegant construction of Blachar, Haile, Matri, Rein, and Vishne. So they defined semi-associative algebras as algebras which are central over the base field. So we have a field F, and we have an algebra with center F. And this algebra has a subalgebra in its nucleus that is a tau. And additionally, to avoid pathological cases, but also in order to be able to use basically Brauer factor sets later, because in Jacobson's book on finite dimensional algebras, he has in chapter 2 a very nice construction on Brauer factor sets. And you can use this for central simple algebras. It's very canonical. If you want to try to work with similar methods in non-associative algebras, it's not enough to assume that the non-associative algebra has an étale subalgebra, which is maximal in its nucleus, whatever maximal means at this point, but it also needs to be cyclic and faithful over E, tensored E, if this étale algebra is E. This way, they later then were able to say that every semi-associative algebra is a form of what they call a skewed matrix algebra. I come to that. Anyway, so here's a definition for an algebra. It's called semi-associative if it has an étale subalgebra in its nucleus and is cyclic and faithful over that E tensored E of this subalgebra E. And one also says A is E semi-associative if E is an étale subalgebra of its nucleus such that A is cyclic and faithful over E tensor E. And one can show, or they showed immediately then, that if A is semi-associative with respect to one étale subalgebra of its nucleus, it's going to be semi-associative with respect to all étale subalgebras of the nucleus. So that basically one can speak of semi-associative algebras without specifying what étale subalgebra we are talking about. And if you want to specify, sometimes it may be important in a proof, one just says E semi-associative. So because of this way of defining semi-associative algebras, the first very nice observation they make is that the dimension is always a square. So we can actually say, we can easily define very intuitively, obviously, for us who know the Brauer group and we know central simple algebras, we can define the degree of the algebra. So the degree is the root of its dimension. Easy to remember, it's just as in the classical case. And then I just list, to get that you get a bit of a feeling, just list some of the results. So say we have a semi-associative algebra of degree n, so that means dimension n squared. And now you see that it looks very similar to the classical theory. Every scalar extension of this algebra will be semi-associative too. And then they call A split if it is a skew matrix algebra. So now what is a skew matrix algebra? I'll tell you that in 3 minutes. But you see from the definition that it seems that the skew matrix algebras will hold the place now of the matrix algebras in the classical Wedderburn theory. So A is split if it is some object which is called a skew matrix algebra. And a field extension K over F splits A if, when we look at this algebra over the extension, this algebra is split, so a skewed matrix algebra. Then we'll show that A is split if and only if F to the N is a subalgebra of the nucleus. So this is the first time where the theory becomes a bit strange looking, because if one thinks of central simple algebras in Wedderburn theory, this is of course something a bit new. And then if we say call the nucleus, so if we say the algebra is E semi-associative, and E is the whole nucleus, not just the subalgebra, it's the whole nucleus, then they show that K over F splits A if and only if it splits this étale algebra E. And they show that any n-dimensional étale subalgebra of the nucleus is a maximal commutative subalgebra of the semi-associative algebra. So if K is a field that splits in a Haile subalgebra in the nucleus, which is in the nucleus of such a semi-associative algebra, and our base field is infinite, then K splits A. So you see that the way they define splitting behavior and so on looks all very familiar, and it feels good because you see that there is this kind of bigger object now where you hope that you can get, but it will be a bigger kind of generalization of Wedderburn theory, one could say, where one hopes one gets lots of analogous statements. So I try not to spam you too much with new definitions, but I'm afraid I will have to give you the definition of semi-central and homogeneous too. So if I take the radical of the nucleus of such a semi-simple algebra, then if you look at the nucleus mod, this Jacobson radical, well, the quotient is semi-simple and the simple components are called the atoms of the semi-simple algebra. So we take the Jacobson radical, mod it out, get a quotient algebra, which is semi-simple, and the simple components of this are called the atoms of the semi-simple algebra. And if all these atoms are F-central, A is called semi-central, and if the algebra is semi-central and its atoms are all Brauer equivalent in the classical sense, then A is called homogeneous. Okay, let's sink in. So basically that means that there are certain semi-associative algebras which are a bit more interesting and certain which are a bit less interesting. We come to that in a second. So now the authors state that the most important example of semi-associative algebras are these skewed matrix algebras that then go on to define and investigate. And these skewed matrix algebras, which will play the role of the normal matrix algebras in Wedderburn theory, also in the generalization of the Brauer group, then they are very important because every semi-simple algebra, when you split it, will become such an algebra. They're all forms of it. They need not be simple, unfortunately, because, of course, the classical Brauer group consists of central simple algebras. But, well, let me see. Okay, so I think I better show you. So the first observation, the first observation I want to make is that every associative, or they made, every associative central simple algebra, as we know them, of degree n has a maximal Haile subalgebra of dimension n and is therefore semi-associative. It's trivially, faithfully, and cyclic. So certainly easiest example of semi-associative algebras are associative central simple ones. The example which I want to discuss today, or which I'm throwing into the game now, are the non-associative cyclic algebras. Because these are also semi-associative, K-semi-associative to be precise. They are simple, they are not homogeneous, and they are not semi-central. So these are probably the, I don't know, I wouldn't say the most difficult ones, but these are certainly non-trivial examples of semi-associative algebras. Another example, now let me abuse my own notation a bit. If I take this Petit algebra construction, and look, I'm taking here a little f, which is t to the m. So I'm taking a field extension of k over f of degree m, and instead of assuming that always I'm taking t to the m minus d, and the d is non-zero, let's just take d equal to 0. So I'm abusing my own notation, so here the d is 0. So this is an associative algebra now, and that is semi-associative, but it's not simple. So this is a canonical example of an algebra that's semi-associative, but it's not simple. It's central, it's not simple, but semi-associative. So this is kind of where it's a bit kind of where one has to be a bit mindful. So, okay. The next example is again due to the Israelis. So this is the definition of a skew matrix algebra. So for that, we need a tensor of degree n of n times n scalars. And that is called a skew set of degree n. And a skew set is called reduced if Cij equals Cjii equals to 1 for all I and j. And if we have a reduced skew set, the skew matrix algebra is the F vector space with basis the matrix unit, the normal ones Eij. So these are the n by n matrices where they have everywhere 0 apart from in spot Ij. There's a 1. And the multiplication is skewed now. You can see here it's skewed. Here we have the Kronecker delta, and then we have theseCijls, this skew set C here, which defines us the skewed multiplication of how to multiply matrices. So I would like to point out the n by n matrices over F appear as a special case here because they are just when we have the skew set 1, everything 1. And these skew matrix algebras are just defined. They are all semi-associative. Not all of them are simple. Not all of them are simple. If you have all the Ci thingies here unequal to 0, they will be simple, but you would lose some simple examples if you just assume they all have to be 0, so non-zero. So one has to be mindful here. Okay. And before I start talking about the semi-associative Brauer monoid, I would like to quickly generalize this definition by Jacobson of generalized cyclic algebras to the non-associative case, again using these Petit algebra constructions. So if I take a central simple algebra B and an automorphism of B, which is when I restrict it to the center of B of order M and has fixed field F, then I can define this algebra where I'm modding out the ideal, the left ideal generated by T to the M minus D for any D in K, where K is the base field of my B. And that gives me an example of a non-associative algebra with nucleus containing B. And that is also called a generalized non-associative cyclic algebra, because if I choose the D to be in F, this is what is written with what is defined in Jacobson's book as a generalized cyclic algebra. So again, a generalization of a very classic construction, which goes back to Jacobson, Albert, and Amitsua. So this is again an example of a semi-associative algebra that is not homogeneous and not semi-central. Okay, so now let's come to this Brauer monoid, the semi-associative Brauer monoid. So we take two semi-associative algebras over F, and we say A is A and B. And we say A is Brauer equivalent to B if there exists a skew matrix algebra and another one such that A tensored the first one is isomorphic to B tensored the second one. So again, you can see this is totally the same as when we are defining Brauer equivalence for central simple algebras. But now the matrix algebras are skew matrix algebras here. And the semi-associative Brauer monoid is then the set of equivalence classes with respect to Brauer equivalence with product given by the tensor product, and the unit element is the usual unit element. So you see that we have an equivalence relation, which is very easy to memorize because it's exactly the same as we know for central simple algebras, just that now we're working with skewed matrix algebras here instead of matrix algebras. And we have exactly the same definition, just that of like the Brauer group, but now it's not a group anymore, it's just a monoid. And the actual classical Brauer group of F is a unique maximal subgroup of this semi-associative Brauer monoid. And so, of course, the next question is, how do the elements in here look like if you look at them in the context of this bigger monoid? So if I have an associative F central division algebra D, say, then I know this defines me uniquely the element in the Brauer group, in the classical Brauer group. And I can also, or they showed that D is the unique member of minimal degree in the equivalence class now of semi-associative algebras. And this equivalence class contains only homogeneous semi-associative algebras. And so my first little contribution is that if I take any field that has a cyclic Galois field extension, then the semi-associative Brauer monoid will be non-trivial. And the class which is defined by this non-associative class, non-associative cyclic algebra is non-trivial, and this class has infinite order. That means the powers of all these elements are all distinct. So that shows you how big these monoids will be. Because I'm not even assuming that this algebra here has to be a division algebra. This is completely irrelevant. So I have just with one cyclic Galois field extension, I will have already an infinitely large monoid here. So then I started to try to understand what happens if I have two semi-associative algebras and they're in the same equivalence class. And so I started to see, so first I started slowly. So say one has nucleus K and the other one has nucleus L, and these are two field extensions. So if they lie in the same equivalence class, then these field extensions must be isomorphic. Okay. So then I tried if I have an E-central simple algebra, and that's the nucleus of the first one, and another one, that's the nucleus of the second one. And again, what happens if these are in the same, I think I made a typo here. So I wanted to write if A and A prime are both in the same equivalence class, which I somehow dropped when I tried to put it all on one slide, but just imagine it stands there, then would basically be the result that E and E prime have to be the same field extension, and the central simple algebras have to be the same in the Brauer group of E. So that tells us in particular, if I have two non-associative cyclic algebras and they are in the same equivalence class, then K and L will be the same. So what I haven't been able to figure out yet is if I have two non-isomorphic cyclic algebras and they're both not associative, do they can it be that they're still in the same similarity class, in the same equivalence class? I don't know. I haven't figured that out yet. But if I look at this, some other relations, so if I, for instance, take a central simple algebra of degree n, a classical one, and I look at the equivalence class of this one and multiply that with the equivalence class of a non-associative cyclic algebra, what I get is the equivalence class of a generalized non-associative algebra. So in particular, I would get this equation here. And although we have a matrix algebra here, this is still not a unit element. This is still non-trivial. And for instance, if the case of splitting field of D, I would get this relation here. So let me finish with some very easy observations. So they noted immediately that, of course, the Brauer monoid of the complex numbers is trivial. So I would like to add the Brauer group of R obviously has is a cyclic group of order 2. We know that R and Hamilton's quaternions are the two classes in there. And if you read that now in the context of this Brauer monoid, one can read it as, well, there are two classes in the semi-associative Brauer monoid that contain the homogeneous semi-associative algebras, and these are exactly the classes of R and of H. Then we know that up to isomorphism, every non-associative simple algebra of dimension 4 with C in its nucleus, if it's simple, must be a non-associative Quaternion algebra. So if we are just if you're interested in these non-pathological cases where they are simple, then we know we have the Quaternion algebras, the non-associative Quaternion algebras now. And so we would have, again, algebras of infinite order in this monoid. And we could also say that since we are working here with prime degrees 2, these elements will always be division algebras, and they will always be division algebras of smallest degree in their classes. So now, because I put you through all these skew polynomials, I want to tell you why. I'm glad I have this time. I wasn't sure. I will stop in 2 minutes, okay? If I have a field of characteristic P, and I have an algebraic duration with a minimum polynomial, then I take the constant field of that one. Well, K over F is a purely inseparable field extension of exponent 1. And Jacobson and Amitsur, they investigated central simple algebras. And you know, when you look in the field case of characteristic 2, well, you have in characteristic 0 and characteristic P, you have the cyclic fields. And then you have the cyclic division algebras. And the kind of counterpart, when you have characteristic P, are the differential extensions, where you have a purely inseparable splitting field. So these are also very, very relevant algebras in the classical theory. And again, these can be generalized because you can take the classical construction, and again, you can choose the D not in F, but in K. And then you will get generalizations of the classical differential extensions, which are, I think they go back to Albert and Amitsur, and called differential extensions, I think, in Jacobson's book. And so then you would get, again, non-associative algebras of dimension P squared. And they're associative again if and only if the D is an F. It's always the same. And the question I want to put out there, and I would be very interested in understanding this better, should the definition of this semi-associative Brauer monoid be perhaps, and I love it, I mean, I understand why it's been the way it's done because of the Brauer factor sets and so on, but should it be perhaps generalized, at least in characteristic P, to include these types of non-associative differential algebras, because they would again reflect the very important differential extensions, which play a huge role in the classical theory in characteristic P. And I don't see why one should omit them. And I think it may not be rich enough, although the thing is already so big, in the characteristic P case at least. And the other thing which I keep wondering is, should one perhaps refine the definition to include only simple F-central algebras, because there are quite a lot of pathological cases one kind of gets into the mix now by not insisting to only look at simple algebras. And so with this, I finish. Thank you very much.
Okay, thank you very much, Susan, for a very interesting and inspiring lecture. Are there any questions or comments?
Yes. Can I make some comments?
Yes.
So first of all, thank you, Susan, for a very, very interesting talk, and also for putting our work in context. As you can see, if you looked at the paper, our motivation—
I love it. I love it.
I guess you've seen the paper, but our motivation was to work with the structure theory of central simple algebras and try to push it as far as we can the non-associative realm. And it's always interesting. All the interesting developments in mathematics come when theory meets examples. So it's both natural and also very inspiring to see that those examples of non-associative cyclic algebras appear in the theory in such a natural way.
I
So
can't tell you how you
have
inspired me. I honestly can't tell you how happy I was when I found the thing on the archive by chance.
So excellent. So I also have some comments on some of the questions. You mentioned one question was if you can distinguish between different cyclic algebras, different non-associative cyclic algebras. So you're touching a very sensitive point in the theory, because we developed, so we do have a mapping from this huge monoid to some, let's say, more combinatorial associative
Yes, I saw.
Something coming from the standard Brauer groups, but your different cyclic algebras with the same K sit on the same point. So you're studying the fiber, and in this sense, this is something we don't know how to do.
Oh, you don't know either, I'm glad.
Yes, at this point, I mean, it's a very natural question.
Yeah, I was thinking of looking perhaps at the corresponding like that one goes to the splitting field and looks at the corresponding skew matrix.
Yes,
that would be my approach.
I mean, it makes sense, but it's very difficult to distinguish matrix algebras, skew matrix algebras. So maybe this could be a direction, but I don't know how easy it's going to be.
Me neither.
And secondly, about this is the example here in the slide. In the associative theory, there is a very robust theory of P algebras, the cyclic algebras in characteristic P. And then if you have a maximal inseparable field, there is always a maximal Galois field, the cyclic
field. Yes, but this is not the case in this setting.
It's a good question. Again, what do you do with these inseparable cyclic algebras? They want to be cyclic, but they are not in the standard sense. So how do you incorporate them into the same theory? It's not clear. And finally, about the last comment on simple algebras, I don't want to make silly mistakes, but I think if you just look at the submonoid of simple algebras and with the same equivalence relation, it should be just a submonoid, including the standard Brauer group. So
then you would get it.
Do it because we want to make the skew matrices as general as possible. But in a sense, you could just impose simplicity on everything.
Yes, I agree. And I was also thinking that perhaps the way forward would be to, at least in characteristic P, which sounds crazy because do we want to make the thing even bigger? But perhaps try to look at the monoid which is generated by basically trying to keep it as small as possible by taking the definition you have already and then just adding these non-associative differential extensions. And I can tell you even why I'm thinking that, because again, there will be a generalization of this one. And again, they behave so very, very canonical that it would be like crazy not to include them.
Huh.
You know, I can send you. I'm just finished writing it up yesterday.
There was a very good reason to assume that the nucleus contains a maximal separable subfield. Because
yes, I see that. Otherwise, it goes crazy because when you look at the tensor products of fields, then you don't have the non-zero divisors anymore. I see that.
But if you can work with non-separable fields in this context, yeah, sure.
No, I see the reason why you did that, of course, yeah.
Okay. Thank you. Any further questions or comments? Let me see. There is one question in the chat, by the way.
Okay, I'm not used to.
Could you give a more intuitive definition for semi-associativity? Even a weaker definition would be nice. This is a question from...
Well, I think this is a super intuitive definition, to be honest. Because if you look, if well, I mean, I think the original authors could be answered that even better, but I think it's totally intuitive because their idea was to work with Brauer factor sets. And that would be the canonical way to force it so that you're able to work with these techniques because this is the minimum you need. The other intuitive way to justify their definition, if I may, is to say, okay, if you look at the canonical, the associative case, you will always have a maximal étale subalgebra. So what's the obvious canonical way to define it? You need to define algebras where you have, again, a maximal étale subalgebra in the nucleus. Right? This is why you did it. Am I summing it up properly?
Yeah, you do, but I can offer another perspective, which is maybe, well, more natural to some people. In the associative theory, a centered simple algebra is precisely the kind of algebra that after extending scalars, let's say to the algebraic closure, you get matrices. So all centered simple algebras are just forms of matrices. And those semi-associative algebras are precisely the algebras which are forms of skew matrices. So if you accept skew matrices, and this is an easier definition because you just take the multiplication rule for matrices and twist something, then algebras that become skew matrices are precisely semi-associative. So you have a natural way to view it in this sense.
Which is what I mentioned. So I thought they wanted yet another one. So I don't know. I'm running out of motivations.
Yeah, thank you. There are also thanks from Florian, who originally asked this question. Any further questions? No more questions in the chat, but it will be interesting to consider what is called Brauer-Rodendijk group, where one considers Azumaya algebras.
Oh, yes.
Which is generalization of central simple algebra.
I would love that because I already did all the Azumaya equivalents. I would love that because I already wrote several papers on basically generalizations of these algebras for Azumaya, and I would totally love that. Brilliant, yes.
Yeah, it could be interesting to develop.
Very interesting because, you know, there are all these algebras which you can also do. And initially I was very scared because Petit always worked over fields. And so it took me quite a while to move away and realize that it's actually possible also to work like with Azumaya algebras. And currently I'm trying and I haven't been able to because of God knows whatever things I had to do. There's a paper where I want to write this differential extension thingies for Azumaya algebras in that setting, which is for me a bit complicated at least. But I already wrote papers on, I don't know, let me see. Because I have, for instance, applications to coding theory. And here I have it. There are generalizations of classical central simple algebras and Azumaya algebras. For instance, non-associative cyclic extensions of central simple algebras. That's from Journal of Pure and Applied Maths. 2019, 21, I did 2 papers on that. And then basically also non-associative differential extensions in characteristic P. And that's what I'm trying to do now also in this Azumaya algebra context. Yeah. Very good contribution. Yeah. Would be great.
Any further questions? There are no more questions and no more questions from the chat.
Uzi, I sent you the preprint as soon as I should send. I want to really have your input, okay? Okay.
Yeah, so let us thank Susan again for for the interesting and wonderful talk.
Thank you.
All the best to all participants.
Happy
of
holidays.
our seminar. Yeah.
Bye-bye.
Bye.